Hello friends, so today we are going to discuss two questions, and these two questions are from rotational motion. In the first question we are given that, one second, okay. So in the first question it states that a cube of side length L rests on a fixed cylinder drum of radius r. Determine the largest value of L expressed in terms of r for which the cube remain in stable equilibrium. So in this case we can just draw an approximate figure, and we are given that we have a cylindrical drum and its position is fixed. Okay, so let us draw a cylindrical drum, and on it we have a cube whose side is L. So this is the cube, and we have to find out that this cube should be in stable equilibrium. So let's assume the cylinder is having a center which is called as O, and this O is our origin. Okay, so we call this as origin, and from here we have our x-axis and we have a y-axis. So this is our x-axis as well as our y-axis. Okay, and the contact point is, let us suppose we call this as P. Okay. And so with respect to this x-axis we are going to measure the angle theta, and we can say, okay, so first of all let us consider that we have a cylinder and its center is considered as origin. O coordinate is 0, 0, and along with this we are interested in angle theta because it is, the cube is having a length L, and this cube has a tendency to, you can say, rotate, and so we need to find out, we have to take an angle theta, and for that we consider that we have a contact point P, and this contact point P is located with the help of theta. Okay, so we can say that our angle theta locates the point P, and locates the point P on the cylinder, and measured from the top. Top means positive y-axis towards the right, towards the right. Okay. So it means we are going to measure this angle theta along this direction. Okay. As it is going to, this point P is going to move. And right now, this value of theta is equal to 0. So we can say if the value of theta is equal to 0, so it means our point P is, we can call this as P naught, and this is at the topmost, or we can say the coordinate of P naught will be equal to 0 comma r. Okay. So it means when this angle, because it is going to rotate, so we are going to call this as angle theta, and when theta is equal to 0, we call this as point as P naught, and its coordinate will be given as 0 comma r. Okay. And a small positive theta moves point P slightly to the right, moves the point P towards right. Okay. And, or we can say clockwise around the cylinder. And unit vector we already know from our, towards our x-axis we can take as this as plus of I, and toward y-axis we can take this as plus of j. And so let us find out what will be the, you can say, the position vector of point P, that is our r of P with respect to theta, because this point P is going to vary as the theta is going to change. Okay. So let's find out. Contact point coordinates and this is our r of P vector and that is our theta. Okay. And so basically this point P is nothing but a point P on a circle. Okay. And if we can represent this point P in terms of our, you can say, parameterized form also. Okay. So this is a circle, we have a center, and this point P is somewhere here. Okay. And the radius of the circle is our r. And if we measure, this is our x-axis, and let me call this as point P as somewhere, and this is our y-axis, and let us suppose this point is somewhere here. And then we measure its position. Suppose this angle is given as phi, therefore we can say that our r of phi will be equal to our r cos of phi I unit vector plus r sin of phi and j unit vector. So obviously when this phi will be equal to 0, and we can say that our the point P will be along our x-axis, and when this phi is equal to 90 degree, the point P will be along our y-axis. Okay, that's the topmost point. And let's find out, because in the question we have assumed that there is angle theta. So let's find out what is the relationship between our phi as well as theta. And let us call this as relation between phi and theta. Okay, because we want this point P should be varying with respect to over theta, not with respect to over phi. Because phi we have taken as with respect to x, and theta we have taken with respect to over, that is y. So this is a minor, you can say. So we want that our theta, we already know that theta is equal to 0 at the top. At the top means when the coordinates are 0, r. Okay. And it increases, and it increases towards right. So it means our theta is going to increase in this direction, okay, and phi is going to increase in the opposite direction. Okay. So phi is increasing in the opposite direction. Therefore, and increases towards the right, or we can also say that our, for the topmost means this point which we already called as P naught. Therefore we can say that at P naught, the value of phi will be equal to pi by 2. So from here we can write that our phi is equal to pi by 2 minus theta. So this is the relationship between our theta as well as our pi. And from here we can get the x coordinate of point P with respect to theta as well as y coordinate of P with respect to theta. Therefore we can say that our x of P is equal to our r cos of, in place of phi we are going to put pi by 2 minus theta, which will be giving us r sine of theta, and we have our y of P, which is our r sine of pi by 2 minus theta. This will be giving us r cos of theta. So it means we get the coordinate of position vector of P with respect to theta is our r sine of theta I unit vector plus r cos of theta j unit vector. So, and this is our position vector for our point P, and as it is going to move from P naught towards our right side, okay, means along our theta. Next we are going to you can say draw or find out the unit normal as well as a tangent at point P. So we have unit normal and tangent at P. Okay. And we already know that our r of P in terms of theta is equal to our r sine of theta and our r cos of theta. And we are going to take a derivative that is going to give us a direction of our tangent. So we derivate it with respect to theta, which will be giving us r cos of theta and minus r sine of theta. Or in the simpler terms, we can take this as r as common. So we will get this as r cos of theta minus sine of theta. From here, we can write that our unit tangent vector suppose that is I unit theta will be equal to cos of theta, and this is, let us call this as a t, because I we use as with respect to our x-axis, and that is our sine of theta and j unit vector. And now we can find out the unit normal. So we can say our unit normal and which this unit normal will be from cylinder center through P, from cylinder center through P, or we can also say the radial unit vector pointing from origin to P, or we can also say it as radial unit vector pointing from origin to P. And let us call this as our n unit of theta, and that will be simple over rp of theta and divided by r, which gives us sine of theta I unit vector plus cos of theta j unit vector. Okay. Now the cube is simply going to rotate. So basically means there is no slipping, only rolling motion is there. So you can say no slipping, only rolling. And this is, you can say that cube rotates while cylinder is fixed. Cube rotates while cylinder is fixed. So let's assume that the contact point moves by angle of theta. Okay. So for that, because we are interested in only the moving the contact point, so initially the contact point is our P naught, which is just above our origin, and let's assume that it moves by angle of theta, and the arc traveled by this is, let us suppose we call this as our S, and R is the radius. And so now initially the P point was as a P naught, and this point is our P now. Therefore we can say that our S is equal to R times theta. And like we said that the cube is going to roll without slipping, therefore we can say that the point on the cube bottom that was in contact moves relative to the cube's center by the same arc length. Okay. So it means this point P, which was basically which is point of contact between the cylinder as well as our here. Initially the cube was here, okay. Then the cube is going to rotate and the position of this cube will be somewhere here. So obviously the distance, sorry, one second, let me redraw it again, because this point, the cube was exactly at the center here, and now the cube is at this position, so its center is exactly going to move by the same distance, that is our S. Okay. Therefore we can say that cube rolls without slipping. Therefore the point on the cube bottom that was in contact moves relative to cube center by the same arc length, So like I said, this was the center of the cube and now the center of cube is here, so it is going to move through the same arc length as the point P, from P0 to P. And we know that the total length of the side of the cube is L, so therefore the displacement, or we can say the linear displacement, will be our L by 2. And from here we can say that if the cube rotates about its center by angle, and let us call this angle as our delta. Therefore from here we can say that the linear displacement at the contact radius L by 2 is L by 2 multiplied by delta. So the cube moves through a arc length of L by 2 times delta, and this point P moves through a distance of S, which is equal to R times theta, and both has to be same, okay, because there is no slipping, only rolling motion is there, okay. So we have to take care of that it is rotating about its center and it moves through angle of delta. And if it is, let me draw it here. So initially, so this is our cube and this is a center, and if it is rotating about its center, so the path that its center is going to follow, it will be something like this. And let's assume that this center moves by a distance of delta. So this arc will be our, because we have a, this will be L by 2 and this is our delta, so this comes as our L by 2 times delta. And therefore we can write that our L by 2 times delta will be equal to R times theta. And from here we can say that our delta is equal to this is 2R divided by L times theta. So this is basically the relationship between the cube rotation with respect to the contact angle rotation. Okay, contact point is our P. So this gives a relationship between the rotation of our point P, because point P is also going to rotate, and it is starts from this P naught to this point P, and this is center of O, and this angle is our theta. So we got the relationship between theta as well as our delta. Now, like I said, that this cube is rotating about its center of mass. Okay, so we can find out its position. You can say its radius vector with respect to theta, and then we move it from there. Therefore, we can say the position of cube's center of mass, and when theta is equal to 0, so when theta is our, let me draw the figure again. So this is our cube, and this is our 0, 0, and suppose this is center of mass, and this is our P, which is equal to P naught, and at this position theta is equal to 0. So if theta is equal to 0, and we know that this is our R, this distance is our L by 2, so the total distance will be coming as our R plus L by 2, and this is when theta is equal to 0. So we can say at theta is equal to 0, and this is the center of mass of the cube. So we can say center of mass is at 0, R plus L by 2, and from here, for any value of theta, we can find out the radial offset as well as you can say tangential offset of this center of mass. Therefore, for general theta, we can write that radial offset which means that it rotates through a radial vector of length that is R plus L by 2. Okay, in this case we are taking for any journal angle theta. Okay, so this is our journal angle theta, and our center of mass is going to rotate somewhere like this. Okay, so new center of mass is somewhere here, and the distance is still will be our R plus L by 2. So we can say the radial offset can be given as similarly point we calculated for our P naught. we can say that our r plus L by 2, and this is our n unit vector at theta, and our tangential offset or we can say it's a tangential translation, and that is same as our r of theta. So this becomes r of theta, and direction we already know is our t unit vector, and this is theta. Now we can find out or write the equation for its position vector. So we can say that center of mass position vector from the cylinder center, from cylinder center. Everything we have to calculate with respect to cylinder center, because in the question it is asked that we have to find out the answer with respect to r, and r is the radius of the cylinder center. Therefore, from here we can write that RCM with respect to our theta will be equal to our r plus L by 2 n unit vector, which is theta dependent, plus r of theta, and this is our tangential with respect to theta. Okay. And in place of this r of theta, we can also write this L by 2 times delta, but we are interested in only r, that's why we are calculating it with respect to our r of theta. And we substitute this component of our n of theta, n unit vector as well as t unit vector. So from here we get this is RCM theta will be equal to r plus L by 2, and this is our sine of theta cos of theta plus r of theta, and we have cos of theta minus sine of theta. We from here we find out the vertical component, that is its y. So from here we can say that height of center of mass, which is nothing but our vertical coordinate, and let us call this as y of theta, will be equal to r plus L by 2 cos of theta plus r theta sine of theta. And we can also check when value of theta is equal to 0. If value of theta is equal to 0, we get this as y of 0 will be equal to sine 0 is 0 and cos 0 is 1. So this is exactly equal to L by r plus L by 2. So it means when theta is equal to 0, this center of mass is exactly at the same distance, that is r plus L by 2. And for now we come to our final part, that is our test of stability. And for test of stability we are interested in finding out its potential energy. That's why we calculated the vertical component, okay, because it is going to move from the height y of theta, that is nothing but our height, okay, and from there we are going to do its derivative and then find out the condition for stability. So we come to the potential energy. And derivatives and stability test. So we can say that the potential energy let us call this as u of theta, will be equal to our mg and h is our height, that is y of theta. And for stable equilibrium, we can say that our stable equilibrium at theta is equal to 0, we get that we need rather y, first derivative of y should be equal to 0 and its second derivative should be greater than equal to, sorry, not equal to but greater than 0. So we can say for stable equilibrium, at theta equal to 0, we need that the first derivative should be equal to 0 and its second derivative should be greater than, it is theta, substituting the value 0, and its second derivative when the value is substituted as 0 should be greater than 0. So let's find out its first derivative. So we know that our y of theta is our r plus L by 2 sine of theta plus r theta times, so it is cos of theta, and r sine of theta. So its first derivative will be equal to, cos will be over minus sine, so this comes as L by 2 sine of theta, and here we can use the product rule and r we can take as common. So first term will be our sine of theta plus theta cos of theta, and we can solve it a little bit because from here we are going to get minus r sine of theta, and this will be plus r sine of theta, so that can cancel out. So from here we get this as minus L by 2 sine of theta plus r theta cos theta. Now we put theta is equal to 0. So we can say our y prime at theta is equal to 0. So we have sine 0 is 0 and this is our theta. So cos 0 is 1, but this is our theta, so that is 0. So we get this will be equal to our 0. Now we got that the first derivative is equal to 0, and we find out now second derivative y double prime theta, and that will be minus L by 2 cos of theta plus, once again we can use product rule, so this comes as r cos of theta minus theta sine of theta, and we can take cos of theta is common, so we get cos of theta is equal to r minus L by 2 and minus r theta sine of theta, and we evaluate it at theta is equal to 0. So cos 0 is 1, so this term is going to cancel 0, so we get this as r minus L by 2, and for stability we know that this should be greater than 0, or from here we can say that our L should be less than twice r. And therefore we can say that the condition for equilibrium, because from here we can just make a draw a conclusion that at borderline is nothing but our L is equal to 2R, we are going to have our equilibrium is neutral. Okay, because when L is greater than 2R, we know that it will be always unstable. This thing we are very sure. Okay. So it means at this particular instant, it will be neutral. Okay, marginal one. So this is the relationship between our length as well as our radius. Come to the next question. And it states that two masses MA and MB are connected by a string of length L lie on a frictionless table. The system is twirled and released such that at the instant of release t is equal to 0, mass MA is at rest and mass MB is moving with the velocity v0 perpendicular to the line connected the center of two masses, the line of the centers. We need to find the subsequent motion of the system and the tension in the string. So in this case, we are given two masses, and suppose this is the string, and we have two masses. This is suppose mass A, and this is suppose mass B. So we have our MA and our MB, and it is set in the motion such that the initially this VA is equal to 0, whereas this B is moving perpendicular with the velocity that is given to us as V0. So VB is having a velocity of V0, and this VA is equal to 0. So let us say that we draw a coordinate system at t is equal to 0, and that t is equal to 0, we put position of this MA is at the origin. So this is our origin, and this is our, and it is connected by length L, and this is our x-axis and this is our y-axis, and this is the position at t is equal to 0. Okay, so you can see at t is equal to 0. So we can say initial setup and coordinate system. Initial setup and coordinate system, and we discuss this at t is equal to 0. So we can say at t is equal to 0, position of mass A is, we have taken that origin 0, 0, and its velocity VA is 0, so therefore we can say it is also 0, 0. And we come to the mass B, so you can say our position of mass B is our 0, L, 0, and its velocity, and the velocity of B is perpendicular to our x-axis, so therefore we can say it will be 0, VB. And the total mass of the system mass of system, that is m, is equal to mass of A plus mass of B. So we can find out the position of center of mass at t is equal to 0. Position of center of mass at t is equal to 0, and we can say, let us suppose this is our RCM 0. So we get this as mass of A 0, 0 plus mass of B L, 0, and total mass is our M. So we get that our RCM at time 0 is equal to this will be our MB times L divided by M, 0. And we can also find out the velocity of the center of mass. So we can say velocity of center of mass, and this will be our VCM is equal to mass of A plus mass of B 0, V naught, total mass is our M. So we get our VCM is equal to 0, and we have this as MB times V naught divided by M. So this is the velocity of center of mass. Therefore, we can say that position of the center of mass at any time t. Say position of center of mass at time t, and we can write it as RCM for any time t will be equal to 0, MB V naught M multiplied by time t. Okay, so this is our position of the center of mass. Now, because there will be a relative motion, because it is as it is trying to, as the entire this mass B is at a different velocity and mass A is at stationary, so there will be a relative motion. So let us shift the center of mass, let us shift the coordinate system to the center of mass frame. So now we are going to take center of mass as the origin, okay, just as it is going to rotate. So let us take that shift to center of mass frame, and this is only to simplify the relative motion. So it is to simplify relative motion. Shift to coordinate system where center of mass is at origin at t is equal to 0. Therefore, we can say that the distance of center of mass from each mass, therefore we can say that our So we have our A and we have our B, and suppose center of mass is somewhere here, and its distance from A is our RA, from B is our RB. No, we cannot. Okay. Because it is going to rotate, therefore distance of center of mass okay, let's think over it. So from here RA or plus RB is equal to L, because total length is given to us as L, and so you can say our position of our A position of our mass A is our minus RA 0, because this is now x-axis, so this is our origin, and this is once again at t equal to 0, and we can say position of MB will be equal to RB comma 0, and this was our position, and we can find out the velocity of center of mass. Velocity of, sorry, now we have to take care in this one important thing, that now we are dealing with center of mass frame. Okay, so therefore we can say that velocities in center of mass frame we can get the velocity in center of mass by subtracting our VCM, which we have just calculated, from our VCM. One second. Yeah, so we calculated velocity of center of mass, that is VCM, and we considered that with respect to our mass, the origin was our mass A. So we can say this velocity with respect to in the center of mass frame, we can write that our velocity of A in the center of mass frame will be equal to 0, 0 minus, and its velocity of A was our mb v0 and divided by our m, and this will be equal to our 0, minus mb v0 divided by our m, and this we can also say will be equal to 0, minus RA v0 divided by L, and similarly we can write velocity of B in the center of mass frame will initial velocity which we calculated is 0, v naught minus 0 comma mb v naught divided by m. And okay, this m is nothing but our ma plus mb. So if we subtract them, mb cancels out, and this comes as our 0 comma ma v naught divided by m, and which can we also say as 0 comma rb v naught divided by l. So we got the velocity of A as well as velocity of B with respect to their center of mass frame. Now we come to our motion in the center of mass. Motion in center of mass frame. And one of the reason of changing the frame of reference is that in the center of mass the total momentum will be equal to 0. And secondly, the string constraint is both the masses will be always at a distance of L apart. Okay, so the distance between the two masses A and B is not going to change, and we know that the velocities are always perpendicular to their line of center. Therefore, from here we can draw an important conclusion that there will be rotational motion about the center of mass. Okay. And in general also it is true that whenever there is no pivot point, the motion, or we can say the rotational motion, is always with respect to the center of mass. In case we have given a pivot point, then we can assume that the rotational motion will be about that pivot point. If the pivot point is not given, if the pivot point is not given, then we can say that our velocity will be, you can say rotational motion is always with respect to the center of mass. Okay, so this is quite obvious. Okay. And so, like I said, you can simply state that we have a rotational motion about center of mass. We have rotational motion about center of mass. Therefore, and if there is a rotational motion about the center of mass, so we can just draw an approximate figure that if this is a string and this is a center of mass and this is a mass A and we have mass B, so both will try to move somewhat like this, okay, because it is going to rotate about the center of mass. And initially the velocity of A was equal to 0 and velocity of B was perpendicular to our this string, that is length L. That was our initial condition. And therefore this VACM and VBCM are nothing but our, you can say, tangential speed. So from here we can write that tangential speed in center of mass frame, and we already calculated the values. So we have VACM, we only interested in magnitude, that is our RA times V naught upon L, and we have our VBCM is equal to RB V naught times L. And from here, because it is uniform circular motion about center of mass, therefore we can write its relationship with the angular speed. So we can say for angular speed omega, we can say that our VACM is equal to omega times RA, and from here we can say that our RA is equal to VACM, we already know, is our RA V0 upon L and divided by RA. So this RA cancels out. This is our omega. So which gives us that angular velocity omega is equal to V0 upon L. And similarly, we can write that our VB, center of mass, is equal to our omega times RBE. From here also we can say that our omega is equal to, and VBCM is our RBV0 upon L, and this is our RB. RB and RB cancels out, so we get from here that our omega is equal to V0 upon L. Okay, and in this case, in order to differentiate, we can also say that this, suppose for A it is omega A and for B it is omega B, just in order to make it clear. But from here we can say that omega A is equal to omega B. So we get our omega A is equal to omega B, which is our omega. So both are rotating with the same consistent value of omega. And now we come to the direction of the rotation, and the velocity of MA will be obviously in the negative y direction and MB will be in positive direction. Okay, so our this A will try to move along negative y and our B will try to move in positive y. So we have our direction of rotation. So we can say that our VA is negative y axis and our VB is in positive y axis. Therefore, we can say that we can find out position of center of mass as a function of time, because it is nothing but now a circular motion. So we can say that our position of center of mass, position in center of mass frame as a function of time. And which we know is our uniform circular motion. And we can say that for our MA, that is mass A, and it starts at minus RA, 0, and which basically means that value of theta is equal to pi, and this is at t is equal to 0. Therefore, you can say that our RA with respect to center of mass at time t will be equal to over Ra, and we have this as cos of omega t plus pi, and we have sine of omega t plus pi. This gives us Ra cos of omega t plus pi will be over minus cos of omega t. So we get this as minus cos of omega t and sine of minus omega t. And similarly for our B. So we can say for mass B, and we know that it starts at RB comma 0, for which theta is equal to 0 at t is equal to 0. Therefore, our RB, center of mass as a function of time, will be equal to our RB cos of omega t comma sine of omega t. And we can also find out whether their velocities are going to match. We simply derivate our R of A, which is going to give us V of A, and R of B, which is going to give us V of B, and we put t is equal to 0. Okay, so we are going to get the same velocity which we just calculated. Now, this we discussed entirely with respect to our center of mass frame. Now we come back to our original frame that was with respect to our RA, or we can also call that as a lab frame. That doesn't make much of the difference. So you can say motion in lab frame, and lab frame was when our mass A was taken as our origin. And so what we do, we transform back into our lab frame. Therefore, our Ra of t will be equal to our Ra center of mass plus R center of mass with respect to time t. Okay, just a simple addition is there, nothing much. So we simply add them, we get minus Ra cos of omega t minus Ra sine of omega t plus 0 comma, and this was our mb v naught m times t, and therefore we get this as Ra of t will be equal to minus Ra cos of omega t, and this will be our minus. Okay, so we have to simply write it, nothing goes away. So we get this as our mb v naught upon m times t minus Ra sine omega t. Similarly, we can write that our Rb of t will be equal to Rb center of mass and our original position of our center of mass. So we get this will be equal to our Rb cos of omega t Rb sine of omega t plus 0 comma mb v naught upon m times t. And from here we get that our rb time t will be equal to rb cos of omega t, and comma, this is simple, we get this as our rb, sorry, not rb, but mb v naught upon m times t plus rb sine of omega t. So we got our value of Ra and Rb, and we already know that our omega is equal to V naught upon L, and our Ra is equal to Mb upon M times L, and our Rb is equal to Ma upon M times L. Okay. And now we come to our final part, that is our tension. And here tension is nothing but it is going to provide our centripetal force in the circular motion when it is in center of mass frame. Okay. So we can say tension in the string and we can say that tension T provides centripetal force for circular motion in center of mass frame. Okay. And which basically means that we have A, B, and the center of mass. So we are going to have this as tension T in the center of mass frame. Therefore, we can write that tension T is equal to over Ma omega square Ra, because this distance is of Ra, mass is of Ma, and here it is our Rb, mass is our Mb. And we substitute Ra as well as omega, we get that the tension T is equal to over Ma, omega A is our V naught upon L whole square, and Ra is our Mb times L multiplied by M. And this is Ma, mass of A, and this square is going to cancel our L. Therefore, we can say that tension T will be equal to, we have this as Ma Mb V naught square, and this comes as L times L. We can write with respect to our B also. So we can say tension T is equal to Mb omega square times Rb. So this will be also giving a tension T is equal to Ma Mb V naught square, and this is Ml. So it means tension constant, which is quite obvious, it is not going to change. So from here we can just summarize the entire thing. First thing is our motion, which was asked in the question, that we can say the motion, it rotates uniformly about center of mass. Rotates uniformly about center of mass, and its angular speed is omega, which is our v naught upon L. Okay. And this, the center of mass translates uniformly with a velocity, and its velocity is 0 comma, we have this as our mb upon m times v naught, and tension we just calculated that our tension T is our ma mb v naught square divided by m times L. Okay, and this will be always constant throughout the motion. Constant throughout the motion. So these were the two questions based on the rotational motion. So this completes both the questions. Thank you.